Okay, so radical chemistry, and as I've said a few times, we're not going to do a lot in chapter 10. Today I'm going to show you the reaction we're going to do, and basically that's it. I'm not going to ask you to draw radical mechanisms. You're just going to need to know this reaction. And it's a way to put how the reaction that's important out of chapter 10 for us right now is how to take an alkane and functionalize it. Okay, I've said before, alkanes really don't do a lot of chemistry. So if you think about chapters 7 and 8, alkenes do chemistry. Alkyl halides do chemistry. Alcohols do chemistry. But an alkane CH bond really just doesn't ever do a reaction. It does, there are some things, but this is also an area where if you could figure out, say, how to take an alkane and put an OH at a particular position, especially if you can do that stereochemically pure, you'd be famous in the chemistry world. So this reaction is just called the free radical halogenation. We take bromine and then light. So this is a nu. It doesn't look like a nu. I can't draw Greek letters. All right, so the energy of a photon is equal to Planck's constant times the frequency of the photon, h nu. So if you see h nu written on a reaction line, what that is saying is there are photons in there, there's light. So this is just light. And then this puts a bromine at the carbon. This puts a bromine on the carbon that would be the most stable radical. Okay, so radical stability, you might recall, I put this up once. Radical stability goes just as carbocation stability goes. Right, so a carbon-centered radical, like let's say this one, I put the bromine here, so that means we have to have had this radical. All right, so if you look at this carbon, it's sharing 2, 4, 6 electrons, and then it's got one lone electron. All right, so 4 valence electrons minus half of 6 minus 1 is 0. So the carbon-centered radical here is neutral, but it's electron deficient and it's really reactive. All right, so again, neutral doesn't mean stable. Neutral means formally neutral. This is an sp3. All right, so it's an sp3 orbital with one electron in it. I guess I should define that. A radical in chemistry is a single electron. So far we've talked about electrons in pairs. You've got lone pairs and you've got bonding pairs. That's it. Radicals, and this is true for atoms and molecules. A radical has a single electron in an orbital. So it's not just like a free-floating electron. It's an orbital. It's an electron in an orbital. There's a really low barrier to inversion here, so the stereochemistry of a radical also goes like a cation. You can expect to get, right, this is going to give us, this is an achiral starting material, achiral reagents. Well, it's achiral too. If this were chiral, it would be racemic. Right? You could wind up, you're going to get this radical, the bromine could come from the top, it could come from the bottom. So it's just like a cation in terms of stereochemistry. All right, so the other thing is radicals generally, not really generally, radicals aren't isolable. Okay, so you're not going to ever get like a bottle of molecules with radicals. There are some exceptions to that. The more delocalization you have, so right, the stability goes as a function, just like carbocation stability. So this tertiary radical would be more stable than secondary radical, which would be more stable than a primary radical, right, which would be more stable than a methyl radical, just like cations. In cations, I tried to hammer home that, methyl cations never form. Primary cations are really rare. Like generally speaking, in a normal lab, so it's not in a vacuum with some weird conditions, primary cations don't really form. All of these form just fine. Right? Methyl radicals form just fine. Primary radicals form just fine. The other thing is delocalization really stabilizes radicals very well. Okay, so a primary benzyl radical is actually more stable than a tertiary radical. So on the left, this benzyl radical, this one electron is delocalized around the ring, and it's quite stable. Obviously, if it was tertiary benzyl, it would be even more stable. Okay, so like I said, this reaction, if you treat an alkane with bromine and light, you're going to put a bromine on the carbon that would be the most stable position. And I'm going to go through this process. But like I said, I'm not going to ask you guys to reproduce this mechanism. And the reason is, radical mechanisms have patterns just the way the ionic mechanisms have. You guys are still trying to get down the patterns of ionic mechanisms. Keep working on that. That's what I'm going to focus on, all right? Exam 3, your final project, you absolutely are going to have to draw more mechanisms for ionic reactions. Right? So that's what you're going to have to draw. In radical chemistry, well, let's just start with it. So radical reactions all tend to go, there are 3 stages. They're a lot more complicated generally than ionic mechanisms. So there's the initiation stage, and in this one, we're making radicals here. All right, so an initiation step, you're going to have reagents that don't have any radicals in them, and the products are going to have radicals in them. So for this, it is the bromine-bromine bond is going to undergo a homolytic cleavage. This is where I always come in here and I'm like, I'm just going to put up this one reaction, and I never can do it. I did my PhD in radical chemistry and photochemistry, still what I study today, so I want to just talk about this. So I'll talk about it a little bit. But remember, really what you have to know is this. All right? Anyway, when a molecule absorbs a photon, I think I've talked about this, an electron, electromagnetic or light, visible light, UV light, if a molecule absorbs that, the physical change that happens to accommodate that energy is a bonding or a non-bonding electron. So bonding electron is just an electron in a bond. Non-bonding is a lone pair. One of those electrons gets promoted up to an antibonding orbital. Okay, so in the case of Br2 or I2 or Cl2, the photon promotes the sigma electron into the sigma antibonding orbital. Right, that breaks the bond. So it's a sigma bond. If you take one of those electrons in the sigma bond and put it in the antibonding orbital, bond breaks. And the way we show this mechanistically, this is why I don't like, I'm going to draw this a little wider here. This is why I don't like showing this, making you guys learn this at this point. Like I said, you're still trying to get the patterns of ionic mechanisms. In radical mechanisms, we have to have an arrow for every individual electron, not pairs. Right? So in an ionic mechanism, you get an arrow like that. And they should be in sequence, right? It's a circuit. You don't ever want to have this or this. So this is for ionic mechanisms. And I've said this before in class, I don't know if you remember it. In an ionic mechanism, each barb of this arrow counts as an electron, which is a weird thing. It's an arrow, it's got two barbs, that's what arrows do. But we actually consider that's an electron and that's an electron. So over here, the arrows do this. Right? Single barbed arrows, and they go away from each other. Right? It's doing exactly what I said don't do over here. So in radical chemistry, it's actually the reverse of this. Right? So in ionic mechanisms, you want a circuit. The head of one arrow meets up with the tail of the other arrow, the next arrow. And you never want to have arrows go away from each other or toward each other. In radical chemistry, it's the reverse. Arrows either go toward each other, away from each other. They never make a circuit. All right, so this is what we're saying with these arrows is one electron in this bond goes to the bromine, one electron goes to the other bromine, and we get two Br dots. All right, and then, and you might have, it's conceivable that you've seen these in an AP course, initiation, propagation, and termination. So here the reaction is going to be an atom abstraction. So the Br dot is going to take an H. Right? So the Br dot makes a bond with one of the electrons in the CH bond. And then the other electron in this CH bond, it's hard to see, goes to make the radical here. So we get HBr. And the tertiary radical. And that's why, so this is just like Markovnikov's rule, right? If you go through a carbocation, you go through the most stable carbocation. In a radical reaction, typically you go through the most stable radical. So a propagation step is going to have radicals on the left, and in the product, you will have radicals. Kind of just changing which atom has the radical. And then I'm going to draw this in. This is the second step. Now, the radical, the carbon radical takes a bromine. Again, you see how the arrows are going away from each other and toward each other, and there's only one barb on them. So the second propagation step is the carbon-centered radical makes a bond to the Br of a Br2. That breaks the Br2 apart. We get a bromine dot left. And this becomes a chain process. And like I said, a lot of radical reactions are chain processes. Did Dr. King talk about this in the plexiglass? Cool. Should have asked that like 10 minutes ago. Okay, so then you've got termination steps, and honestly, termination steps are boring because then your reaction's over. In a termination step, you're going to have radicals on the left, go to no radicals in the product. Easy ones here would be Br dot plus Br dot going to Br2. Although in this reaction, that wouldn't necessarily stop it, because then light could just hit that again. You can have two carbon radicals make a carbon-carbon bond. You could have a carbon radical and a bromine radical make product, but not produce another radical, so then the chain stops at that point. Like I said, I'm not, this is important to know. So after, I don't know, I haven't quite decided what we're going to do after Thanksgiving yet. We're not going to do nothing. It'll be something on Zoom, but if you've read about the ozone layer in your life, the reactions of halogenated organics in the upper atmosphere go through radical chains, right? So just a little bit of light can do a lot of damage. So this is an important mechanistic paradigm to know. But like I said, the mechanisms you're going to have to write on exam 3 in a little over a week will be ionic. It'll be like this, so focus on that. I mostly want you to know that you can do these halogenation reactions. And it's always going to go on the carbon that makes the most stable radical. All right, so let's look at this. So let's do draw the product of that reaction. How do you know if a molecule absorbs visible light? What's that?
It's kind of carbon.
No. It's what? No. This is easier. This is not a college question. This is a grade school question.
If it has a color?
It's got a color. So if you've ever seen bromine, how many of you have seen iodine? Iodine's a better one.
Oh.
Probably all of you have seen iodine. What's that? No, what was
Isn't that the one that like tests for like starch and like potatoes and stuff? And like bio?
That's oddly specific.
That's like what I think of. When you have to like test it and like
So in biology class, they don't call it iodine, it's just like
I think it was like
test
iodine
solution.
solution and like tests for like starch.
Biology really likes to act like chemicals aren't chemicals. But, I like, some of you are going to be bio majors, right? Like it's just a foregone conclusion that's going to happen. I'm working hard, but I can't stop everything. I feel bad. I made fun of business school last time. My natural environment is making fun of bio majors. Right? And not majors, like professors. I like to make fun of them too. Yeah, so no, iodine there. How many, I don't know if you've had, this is always, I'm not supposed to, at the beginning of the semester, like, you cannot ask them if they have COVID. Okay, I'm going to ask them if they have COVID. It's like the only question I care about, but I won't ask. If you've ever had surgery or any kind, and that iodine is a really good sterilant. So there's this kind of reddish stuff they'll like spray all over your skin before they chop you up. That's iodine. And the way it works is iodine's colored. It's kind of purplish. Iodine crystals are really pretty. Bromine, Br2 liquid is this real, I think it's a very pretty kind of reddish orange color. Anyway, both of those molecules, if you put them out in room light, absorb room light. They're colored, so they're absorbing light. When they absorb light, you get this reaction. And that's how they sterilize things. Radicals are actually really toxic generally. They're extremely reactive. More reactive. If you had a choice of having like Br dot poured all over you or having hydroxide poured all over you, you'd probably go with the hydroxide. It's close. It would depend how close you are to like a safety shower. But these are things you got to think about when you work in a lab, right? Radicals are really quite toxic. I mentioned this the other day with peroxides. That's how hydrogen peroxide sterilizes cuts. heat of your body is enough to break the OO bond, you get hydroxyl radicals. And those just go in and they rip hydrogens out of DNA and out of proteins. And on the scale that we use them, okay, it would be possible to kill a human with iodine, but you'd have to like drown them in it. Whereas if there's bacteria there, right? Bacteria are single cell, you do a little bit of damage, they're a lot more susceptible. It takes a lot less to kill. So these the things that are sort of general sterilants are almost always bad for you. Bleach and ultraviolet and iodine. Anyway, all that mostly comes from just things that have color in them are absorbing light. And when they absorb light, something's got to happen to the molecule. I never did tell you what the answer was, did I? All right. So you've really got a couple of choices here. There's the tertiary position, and what I erased down here was telling you the benzyl position makes a more stable radical than a tertiary. This is going to be a secondary benzylic versus a localized tertiary. You might also be wondering here, but remember with cations, you don't want to have cations on carbons that started sp2. So by far, the best radical you can make out of this molecule is right here. And so the product would be this. Yeah. And it would be racemic. And then you can do all the stuff you've learned to do with alkyl bromides. That molecule right there can do an elimination. You can do a substitution. If you do an elimination, you get an alkene. You can do all the reactions in chapter 8. Right? So this is, organic chemists are sort of looking for a toehold where we get organic starting materials from two places. One is from the biological world, right? So you can take plants or animals, grind them up, and you can pull out organic molecules. Plants and animals are nice because they tend to give us optically pure, right? They give us single enantiomers. The chemistry of life is carried out by enzymes. Enzymes are chiral. They make optically pure products. The other way to get organic material is to pump it out of the ground. It's petroleum. We crack it down to really simple organic molecules, hexane, octane, that sort of thing, benzene. And then we have to functionalize them. There's not much you can do with octane other than put it in your car and drive around. So if you want to make molecules, make more complex molecules out of them, you have to functionalize them. And that's why this reaction is really important. All right, so I'm gonna finish here. This is all we're doing in chapter 10 before the exam. If you take an organic molecule, treat it with bromine and light, then you get a bromine on the most stable radical. And if you overdo it, right, the rest of these, we've got a bunch of secondary positions. If you leave this reaction go a long time, if you use a large excess of bromine, you can brominate those secondary positions too. If you look in the book, you can do this reaction with chlorine. That favors products. Chlorine's a lot more reactive, and it turns out that the selectivity is much less. So with bromine, you're pretty much guaranteed to get one, maybe 2 or 3 products, but you're not going to get them all. With chlorine, if we did this reaction with chlorine, we'd put a chlorine on every carbon, basically. And you'd have 20 different products. Yeah.
So if the reaction you had circled was like a benzene ring instead, would it go on the end of the...
Yeah. So if this was a benzene, you'd only get it there.
Okay, because you're not going to break like one of those double
Right,
bonds.
and I said this in class yesterday. I don't remember where all I've said this. I need to say it more and more. In chapter 8, we do a whole bunch of reactions with alkenes, carbon-carbon double bonds. This looks like 3 alkenes. Okay, this is not 3 alkenes. This is a benzene ring. So if we take, so no light, just Br2, right? If those were alkenes, you'd expect to get Br added anti across all those double bonds. Nothing happens. Osmium tetroxide, no reaction. Right? Benzene has this special, I don't want, it's not really, this is not the right terminology, but it's got kind of this special quantum mechanical stabilization. And you'll see that in Orgo 2. You'll talk a lot about it's called aromaticity. And you'll see this a lot in orgo 2. But right now, benzene's not going to do any of the chemistry we've been talking about. Okay? But the benzyl position, the carbon bonded to a benzene ring, does a lot of this stuff really well, right? Because any charge you put on that position, any single electron you put on that position gets delocalized around the ring and it's stabilized. How we doing?
3 minutes.